I guess it's clear, right? Perfect. Then hello, everyone. I'm Can. I'm a PhD student in the Safari Research Group led by Professor Onur Mutlu at ETH And today I'll present our work RawHash, enabling fast and accurate real-time analysis of raw nanopore signals for large genomes. Nanopore sequencing is a widely used sequencing technology. It can sequence large fragments of nucleic acid molecules up to more than 2 million bases. It offers high throughput, it is relatively cost-effective, and it also enables real-time genome analysis, which is the main focus of our work. Let's look at how real-time genome analysis with nanopore sequencing works. This figure shows the sequencing of a nucleic acid molecule while it moves through a tiny pore called nanopore. As the molecules move through a nanopore, ionic current measurements are generated at a certain throughput. These measurements correspond to different nucleotides in the molecule and form the raw signal data to analyze. And computational tools can then analyze all of these signals at a speed that matches the throughput of the raw signal data generation, which we refer to as real-time analysis. And based on this analysis, we can make some real-time decisions. These decisions can stop the sequencing process early if sequencing of a read or the entire sequencing run is unnecessary. Real-time genome analysis provides two important benefits. First, we can overlap the sequencing time with the analysis time, reducing the latency of the entire process. Second, we can stop sequencing of a read or the entire sequencing run, and this capability essentially can significantly reduce the sequencing time and potentially the cost, making genome sequencing more efficient and cost-effective. There are several challenges to achieve real-time genome analysis. First, we need to maintain rapid analysis to match the throughput of a nanopore sequencer. This is essential for enabling real-time analysis. Second, we need to make timely decisions to stop sequencing as early as possible. Otherwise, unnecessary sequencing can waste time, power, and money. Third, we need to ensure accurate analysis from noisy raw signal data. Noise in raw signals can cause variations even among the signals from identical nucleotides. Despite this, raw signal data holds richer information than just individual bases. Fourth, we need to achieve efficient computation for scalability and portable sequencing that is often connected to resource-constrained devices such as mobile devices. Now that we have some basic background on real-time analysis with nanopore sequencing, let's go over with an executive summary of our work. Real-time analysis of raw nanopore signals lacks the necessary accuracy and speed for large genomes. This issue hinders us from fully exploiting the potential of nanopore sequencing. And our goal in this work is to enable fast and accurate real-time analysis of raw signals for large genomes. To this end, we make two key contributions. First, we introduce the first hash-based mechanism for quick and accurate real-time analysis of raw nanopore signals for large genomes. Second, we introduce a novel technique called sequence until that can accurately and dynamically stop the entire sequencing run if further sequencing is not necessary. Our extensive evaluations across 3 use cases and 5 genomes of varying sizes, including a large genome such as the human genome, shows that RawHash outperforms the existing state-of-the-art works. It offers an average throughput that is 25.8 times and 3.4 times better than the existing 2 state-of-the-art works. It also delivers mapping results that are up to twice as accurate for large genomes. And with the sequence until technique, we can reduce the sequencing time and potentially the cost by 15 times. Before we dive into our mechanism, let's look at the existing 2 main solutions for real-time genome analysis. First one is to use deep neural networks, or DNNs, to translate the signals to bases. And these base code sequences are then analyzed in real time using, for example, a standard read mapping step. DNNs provides less noisy analysis from base code sequences. However, these solutions come with high computational and power demands, which particularly create challenges for portable sequencing. Second common solution is to directly map the raw signals to reference genomes without necessarily using DNNs or base calling mechanisms. These solutions provide an alternative and efficient ways to analyze raw signal data in real time. However, when mapping raw signals to reference genomes, the size of the genome plays a crucial role. For small genomes, we have fewer candidate regions to analyze per read, which can allow for accurate mapping and high throughput. However, when we deal with large reference genomes, the number of regions to check per read increases substantially. This leads to 2 main challenges, essentially. First, the prior probabilistic mechanisms such as uncode can result in inaccurate mapping due to large number of regions to choose from. Second, the mechanisms such as SIGMAP that calculate distance on many regions per read significantly reduce the mapping throughput. We find that these existing solutions are inefficient or inaccurate for large genomes. Now that we covered the existing solutions and the problem, let's dive into our work, RawHash. Our goal in this work is to enable fast and accurate real-time analysis of raw nanopore signals for large genomes. To this end, we propose RawHash. We make two key contributions. First, we provide the first hash-based search mechanism to quickly and accurately map raw nanopore signals for large genomes. Second, we propose a novel technique called sequence until that can dynamically and accurately stop the entire sequencing run at once if further sequencing is unnecessary. I'll first explain the hash-based search mechanism in RawHash. The key observation in RawHash is that the identical nucleotides generate similar raw signals. And one way to identify these similarities is to calculate the distance between them as SIGMAP does. However, this becomes too slow for large genomes in the existing state of the artwork. Instead, we generate hash values from raw signals and quickly match them to identify similarities. And we find two key challenges to overcome. First, to match the hash values to each other, we need to generate the same hash value from similar raw signals. Second, to facilitate quick similarity search, we need to find accurate, but also fewer similar regions in a large space of reference genome. To solve these challenges, RawHash has 4 key steps in its mechanism. We start by converting the reference genome and raw nanopore signals into signal representation of k-mers known as events. Second, we quantize these events to reduce the variation effect in raw signals. Third, we generate the hash values from these quantized values to enable fast similarity identification by matching the hash values. In the last step, we perform chaining and mapping based on the matching regions between raw signals and the reference genome. The left side of this figure refers to our offline indexing step for reference genomes, and on the right side, we show the steps that we take when mapping the raw nanopore signals in real time. Let's go over these steps, starting from the first step that converts the reference genomes and raw signals into events. In nanopore sequencing, an event is a specific segment of the signal that corresponds to a particular k-mer or sequences of k-nucleotides. Event detection is the process of identifying these segments that are generated when sequencing a particular k-mer. And the start and end positions are usually marked by abrupt changes in the signal, and statistical methods are typically used to identify these abrupt changes in the signal. An event value is the average of all signals within the same event. Now that we know what events are, let's look at how we convert the reference genome and raw signals into events so that we can enable comparison between them. To convert the reference genome into events, we use a lookup table known as k-mer model. This model provides an expected event values for each possible k-mer. And it is pre-constructed based on the characteristics of nanopore sequencers. We use this k-mer model to convert all k-mers of a reference genome to their expected event values, followed by a normalization step to generate the normalized event values to enable for comparison purposes. So we simply represent the reference genomes as series of their events rather than their k-mers. To convert signals to events, we use an event detection mechanism. This is done by performing a statistical test or segmentation to identify the abrupt signal changes generated as molecules move through nanopores, followed by mean calculation and normalization again. In high level, we assume that the consecutive events represent consecutive k-mers. And now that we have a series of events generated for both reference genomes and raw signals, let's explore if we can directly match these event values to each other to identify similarities. To explore this, I'll now go over the second step of our mechanism, the quantization step. Remember our observation that the identical k-mers generate slightly different raw signals. So this presents a challenge as we cannot directly match event values to each other, since this will not be accurate due to variations. The key idea to overcome this challenge is to quantize the event values. So this enables us to assign the same quantized values to similar event values. I'll now move to the third step in our mechanism, which generates the hash values from these quantized values of events. An event typically represents a very small k-mer from 6 to 9 characters. So this results in a challenge as these short k-mers can appear in a large number of regions in the reference genome, making direct matching of quantized event values infeasible. Our approach to this challenge is to form longer k-mers from consecutive events. By packing the quantized values of these events, quantized values of events into a single value. And to efficiently store these packed values, we generate their hash values using a hash function. The benefit of this approach is that it allows for direct matching of larger regions from their hash values, enabling swift identification of similarities. Now, with the fourth step of our mechanism, let's cover how we put all these steps together to perform real-time mapping. So in both indexing and mapping steps, we generate hash values from reference genomes and streaming raw signal. For the reference genome, we store the hash values and their positions into a hash table to enable efficient queries during mapping, which also concludes our indexing step. Then the hash values that are generated for raw signals in real time are queried using this hash table to quickly identify the matching positions between the reference genome and the raw signals. We then perform chaining between these matching positions and identify the mapping accordingly if there's a good chain of matches. In real time, we continuously decide if we should continue mapping a read or not based on the mapping information we generate so far. And if yes, we simply retrieve the next chunk of data generated in real time and continue our mapping. And if not, we can simply tell the sequencer to stop sequencing a read or the entire sequencing run using the read until or run until functionalities of Nanopore sequencer, respectively. This was the first part of our contribution we make in RawHash. In the second part, I'll very quickly describe the sequence until mechanism. The problem we tackle with the sequence until mechanism is to avoid unnecessary sequencing that can waste time, power, and money. So to mitigate this, the sequence until mechanism continuously evaluates if further sequencing of the entire sample is essential to achieve the similar accuracy we would achieve with full sequencing. If not, we can stop the sequencing early without sacrificing from accuracy significantly. This method solves the potential to significantly cut down both the time and cost associated with sequencing. Also, the sequence until mechanism is compatible with any raw signal analysis tool. To provide a practical example, let's consider the relative abundance estimation use case. Considering this particular use case, the sequence until mechanism works in several steps. We continuously generate relative abundance estimation after every sequencing of every n reads. And we always retain the most recent t estimation results. The next step involves detecting any outliers in these results by performing a cross-correlation between them. So if you find no outliers, it indicates that the recent sequencing of reads could not change the estimation results significantly. In such a scenario, no new significant information is likely to be gained from further sequencing. Therefore, we can make the decision to stop this entire sequencing run. If there's an outlier, we simply keep sequencing as new reads keep changing results. So I'll now move to our evaluation. We compare RawHash with two state-of-the-art works, Uncode and SIGMAP. And we have three use cases for real-time genome analysis. So read mapping maps the reads to reference genome. Relative abundance estimation identifies the ratio of each genome in a particular sample. We also briefly show the benefits of sequence until mechanism for this particular use case. And the contamination analysis identifies if a sample is contaminated with a particular genome by mapping the reads to that genome. Our evaluation metrics include throughput, which is basis process per second, the potential reduction in sequencing time and cost, and accuracy. For accuracy, we map the base code reads of corresponding raw signals using Minimap2. And based on this, we calculate precision, recall, and F1 scores. And for relative abundance estimation, we additionally calculate the distance of each estimation that each tool generates to the ground truth estimations. We use 5 real data sets, including large genomes such as a human genome. For relative abundance estimation, we combine both the reads and the reference genomes used in all data sets from D1 to D5. And for contamination analysis, we combine the COVID-19 and the human read sets and map them to the COVID-19 reference genome. On the y-axis of this figure, we show the throughput results from each tool, and inside the bars, there are improvements over the throughput of a Nanopore sequencer, which is around 400 bases per second. On the x-axis, we show the data sets we use to generate these results. To achieve a real-time analysis, the throughput of the computational mechanism must be faster than the throughput of a Nanopore sequencer. So if a bar below the red line on this figure, this indicates a failed real-time analysis due to slower analysis than Nanopore generates data. We observe that RawHash provides 25.8 times and 3.4 times better average throughput compared to Uncode and SIGMAP respectively. This is essentially achieved by efficient similarity search with RawHash. We also find that SIGMAP cannot perform real-time analysis for large genomes due to costly distance calculation that it offers. We also look at how quickly RawHash and ENCODE stop sequencing based on the number of bases they process before stopping the mapping of a read. These number of bases are shown on the y-axis of this figure. And fewer bases to sequence provides an estimation on how much we can save from the sequencing time and potentially the cost. So lower is better here. We find that RawHash reduces the sequencing time and potentially the cost for large genomes up to 1.3 times compared to ENCODE. This shows that ENCODE is not scalable to larger genomes, potentially due to increased noise with larger number of regions, which challenges its probabilistic decision. We also evaluate the read mapping accuracy for each dataset separately and the datasets combined for relative abundance estimation and contamination analysis. We find that RawHash produces the best accuracy in all metrics for large genomes, up to 2.13 times for the F1 score compared to ENCODE and SIGMAP. So this is essentially because we can fine-tune the sensitivity-related parameters in RawHash while still matching the throughput of Nanopore sequencer, which is specifically not the case for SIGMAP, as even the default parameters of SIGMAP falls behind the Nanopore sequencer. For smaller genomes, the accuracy of RawHash is on par with ENCODE and SIGMAP, although these tools usually provide better accuracy than RawHash. Last, we look at the relative abundance estimation results. This table shows the abundance estimation that each tool makes based on their mapping and their Euclidean distance to the ground truth estimation, and lower is better. We find that RawHash provides the best relative abundance estimation closest to the ground truth estimations. So this is consistent with the best read mapping accuracy results RawHash provides for large genomes, as this particular use case also includes a large reference genome dataset. We invite you to check our paper for more discussion on the results we show regarding the real implementation of sequence sample using RawHash. We show that we can sequence only 7% of the entire sample while providing highly accurate results similar to using the entire sequencing dataset. We also show the simulated benefits of sequence sample, not just on RawHash, but also on ENCODE. We find that sequence sample can provide significant benefits for ENCODE too. You can find more results such as mapping time per read, overall computational resources required by each tool, performance breakdown of steps in RawHash, and details on all our mechanism, configuration details, and trade-offs between the DNN-based approaches and raw signal mapping in our paper. You can use the QR code to access our paper published in Bioinformatics as part of the proceedings of ISMB and ECCB. And you can use this QR code to access our source code. RawHash supports all major raw signal formats such as FAST5, POT5, SLOW5, and BLOW5. We provide easy-to-use scripts to download all of our data sets and to reproduce all of our results. You can also write your own outlier function to improve the sequence until, and we continuously improve our implementation, and our upcoming feature is to direct integration to the MinNode API. And last, although we have not explained it, our hash-based approach enables using the existing sketching techniques, such as minimizers, strobmers, and fuzzy seed matching with blend, which was not possible before for mapping raw nanopore signals. This is because we can now identify similarities using simple hash matches from hash values. In fact, we already implement the minimizer sketching technique in RawHash, but we leave its explanation and evaluation for future work. Let's conclude. We provide the first hash-based mechanism for quick and accurate analysis of raw nanopore signals for large genomes. We also propose sequence until that can accurately and dynamically stop the entire sequencing run if further sequencing is unnecessary. RawHash provides significant improvements in terms of the overall throughput and also the accuracy for large genomes, and sequence until can reduce the sequencing time and cost by 15 times. We believe that there are many opportunities lie ahead for analyzing raw nanopore signals in real time. For example, we can now use many hash-based existing sketching techniques for raw signals, now that we can use hash values to identify similarities between them. Indexing in RawHash is very cheap. This means that there can be many new use cases by enabling on-the-fly index construction. In general, we should rethink the algorithms to perform downstream analysis fully using raw signals without necessarily base calling them to use their richer information and reduce the analysis latency, sequencing time, and cost. With that, I'll conclude my talk, and I'm happy to take questions.
Thank you very much. Does it work on RNA sequencing and specifically to detect epitranscriptional events? And there are hundreds of those events. And how do you deal with those ones?
That's an excellent question. So we haven't looked at the RNA-seq data yet. We only worked on DNA-seq data using R9 flow cell versions. So this is not in our paper, but What we also observed is that we can actually use any k-mer models, for example, even directly from R9 flow cells, and RawHash actually provides good enough results, let's say, similar to the results that we have. So I'm assuming that although we haven't confirmed it, I think RNA-seq data should also work in RawHash. But this requires further confirmation. Yeah.